All right, so here's the video for the Unit 9 practice test. So question number 1 says, a significance test allows you to reject a hypothesis HO in favor of an alternative HA at the 5% level of significance. What can you say about the significance at the 1% level? Well, in order to reject at 5%, that's an alpha of 0.05, your p-value would have to be less than that. So, for instance, an alpha of 0.04, a p-value of 0.04, we would reject our null hypothesis, right? But if we had a p-value of 0.001, we would also reject our null hypothesis. Well, now it's saying, well, what if you change your alpha level to 0.01? Well, if we're rejecting at 5%, that doesn't necessarily mean we're going to reject at 1%. It just depends on what the p-value is. So like I said, at 5%, 0.05, you can reject at 0.04, but you can also reject at 0.001. So in that case, we're going to say the answer is E. The answer can't be determined from the information given just because we don't know what the p-value is. All right, number 2 says, in a test of HO, mu equals 100 against HA, mu is not equal to 100, sample size of 80 produces a Z of 0.8 for the value of the test statistic. What is the p-value of the test? Okay, so p-value, in order to find that p-value, we're going to look up our test statistic. And then since it's not equal to, that means we're going to look at the negative side and double it. All right, so looking up our p-value here, we have negative 0.8, that's 0.2119, and we're going to double that. So it's going to be 2 times 0.2119. So when we double that, we get 0.4238, which means our closest option is going to be D, 0.42. All right, next question. So same type of question, but now it's giving us a test statistic of negative 2.4. So we're going to do the same thing. However, since the p-value is already negative, we could just look up negative 2.4 and we're going to double it. All right, so test statistic of negative 2.4 is 0.0082. So it's 2.0082, which is going to give me 0.0164. So the closest option is going to be 0.016. It's going to be D. Okay, number 4 is a type 1, type 2 error problem. So it says to determine the reliability of experts used in interpreting the results of polygraph examinations in criminal investigations. 280 cases were studied. The results were, and it gives the result. So it says if our null hypothesis is the suspect is innocent, and our alternative is that the suspect is guilty, a type 2 error would be, well, in a type 2 error, you fail to reject the null when the alternative is true. So in that case, we're basically saying, oh, we didn't find anything, but we missed something. So in that case, we would say, oh, we decided that the subject is innocent, however, they were guilty. So type 1, again, like I said, or type 2 is basically concluding the null when the alternative is true. So concluding that they're innocent when they really aren't. So in that case, is going to be C. All right, the next question is another p-value problem. It gives us a Z of 2.45, and our alternative hypothesis says greater than. So in that case, we're going to look it up in our table and subtract from 1. So we're going to look up 2.45. So 2.45 is going to be 0.9929. So for this p-value, it's going to be 1 minus 0.9929. And that's going to be 0.0071. So the correct answer is B. All right, number 6. So this is basically asking us to find the p-value for a particular case. We have X bar, we have mu, we have S, and we have N. So first thing we need to figure out is if we're using Z or T. Well, since we're not given our population standard deviation, we know that we're going to be using T. Also, our sample size is less than 30. So that's going to be our test statistic. So our test statistic is going to be X bar minus mu, so it's 13.82, minus mu, which is 14, divided by S over the square root of N, so 0.24 over the square root of 16. So that gives us negative 3. And in this particular problem, we need to look at our T table. So our degrees of freedom is n minus 1, so 16 minus 1 is 15. So now we're going to go to our t-table. Okay, so here we are at our t-table. Degrees of freedom is 15. So we're going to ignore the sign since we're just looking at the opposite side. So that means our p-value is going to be, or test statistic is between these two. So that means our p-value is between 0.0025 and 0.005. So p-value between 0.0025 and 0.005. So that's very, very small. So if we're looking to see when can we reject, well, we can basically reject at the lowest level of significance because 0.005 is less than 0.01. So that's going to be D, where we're going to reject our null at the significance level of 0.01 level. Number 7 says a type 2 or type 1 error in the previous question would mean, so remember type 1 is when you reject the null but the null is true. So we would conclude that the bags are being underfilled when they actually aren't. So that's going to be A. So concluding that the bags are underfilled when they actually aren't. All right, the next question says a random sample of 100 voters in a community produced 59 voters in favor of candidate A. The observed value of the test statistic for testing the null hypothesis, P equals 0.5 versus the alternative P is greater than 0.5 is, so first of all, this problem is proportions, which means that I should be using Z. So that means I can eliminate option C and option D. Now we just need to plug in our values. So P hat in this problem is 59 over 100, which is 0.59, which looks to be true for both of these, minus mu, so that's correct. So then we have to look and see what we plug in the bottom. Well, in our formula, remember that it's P times 1 minus P. So in the denominator, it's P times 1 minus P, so it should be 0.5 times 1 minus 0.5, which is this option right here. So the correct answer is B. So we don't use P hat in this formula, we use P, so that's why B is the correct answer. All right, number 9 says a group of nutritionists is hoping to prove that the new soybean compound has more protein per gram than roast beef, which has mean protein content of 20. Random sample of 5 batches of soy compound have been tested with these results. What's the appropriate statistical hypotheses? Okay, so first of all, let's decide Z versus T, so then we can narrow it down to 2 options. So in this problem, I have a sample size of 5, which is less than 30, which tells me that I should be using T. So I should eliminate B, I should eliminate C and D, since I know that I need to be using T. So in looking at these 2 options, the test statistic is the same, but then if we look at our alternative hypothesis, we need to decide if it's less than or greater than. So since it says more protein, we know that we should be using greater than, so the correct answer should be B. The next question looks like we are writing the appropriate hypotheses for this particular example. So Excellent Drawn Company claims its aspirin tablets will relieve headaches faster. So that looks like a keyword, faster than any other aspirin on the market. To determine whether the claim is valid, random sample size of 15 are chosen. Let's see, 30 randomly selected persons suffering from headaches, number of minutes. Okay. So it looks like we're comparing 2 groups. So it's a 2 sample mean problem. And it says we're using a significance test to determine whether Excellence aspirin cures headaches significantly faster in less time than Simple's aspirin. So our null hypothesis, I know looking through my answer choices, there's 2 options I could definitely eliminate, E and D, because we know that our null should always be an equal sign. So then we have to decide between these 3. It says Excellent cures headaches significantly faster, so in less time. So that means it should be Excellent is less than Simple. So that's going to be option C. Okay, so number 11, we are calculating the expected count in a 2-way table. So it says employees under the age of 25 who had a burn. So we're calculating the expected count for this. So to calculate expected count, you have to do the row total is row total times column total divided by n. All right, so let's first figure out what our row totals are. So we're going to add across the top. That's going to be 31. And then we have to add the column total. So that's going to be 30. And then n in this case is 117. So now to calculate our expected count, it's going to be 31 times 30 divided by 117. That's going to give me 7.9. So the expected count for employees under the age of 25 who had a burn is going to be C, 7.9. Okay, so now number 12 says are all employees equally prone to having accidents? To investigate this hypothesis, a researcher looked at a light manufacturing plant, classified the accidents by type and age of the employee. It says the chi-square test gave a test statistic of 20.78 and a p-value of 0.00003. Which of the following statements is correct? So A says we cannot proceed with inference because 2 of the entries are less than 5. That is not true. B says the purpose of the study is to see if the type of accident depends on gender. That's not true because we're not looking at gender, we're looking at age. The number of degrees of freedom is 6 minus 1, which equals 5. No, because remember the way we calculate degrees of freedom for this type of test is row minus 1 times column minus 1. So the amount of rows there are is 2, and columns is there's 3. So the degrees of freedom in this case would be 2. D, according to the central limit theorem, I already know that this is incorrect because we don't use central limit theorem for chi-square test, and we don't use a normal distribution, which means that E should be correct, but let's just check. Small p-value tells us there is evidence of a strong association between age and type of accident. That is correct because we know when we're doing a chi-square test, our null hypothesis is that there's no association between the variables, and the alternative is that there is an association. All right, the next question is a hypothesis test question. So it gives us average IQ is 100, standard deviation of sigma equals 15. So right away I know this is a problem about means. Principal at a certain school claims that the students in his school are above average intelligence. We have a random sample of 30 students, mean score of 108. We want to know if there's sufficient evidence to support the principal's claim. So this looks like it is a one sample mean problem where we're comparing these students' scores to what the average IQ is. So let's identify the symbols first. So mu in this problem is 100. In this problem, we are given sigma, that's equal to 15. N is 30. And then X bar in this problem is 108. So for the hypotheses, since it's a one sample mean problem, our null is that mu is equal to 100. Our alternative hypothesis, they're claiming that the students are above average, so that means it's going to be greater than 100. And mu equals the average intelligence, or mean intelligence. Or average IQ, I guess I should say. So now let's check our conditions. So the independent condition is big N, which is going to be all students, is greater than or equal to 300. That's definitely reasonable. The normal condition is that N is greater than or equal to 30. So 30 is greater than or equal to 30. That is true. So that means it's approximately normal. And then random, let's see, it does say a random sample. So that's stated. All right, so now let's do our test statistic and p-value. So in this particular problem, it is a problem about means. We are given the population standard deviation sigma, and our sample size is 30, which meets that condition as well. So that means in this particular case, we're going to be using z. So to calculate, it's going to be 108 minus 100 divided by 15 over the square root of n, which is 30. So that gives me a test statistic of 2.92. And now to find our p-value, we're looking for the probability that z is greater than 2.92, which means we're going to look up 2.92 in our table and subtract it from 1. All right, here's our z table. So 2.92 is going to be this value right here, so 0.9982. So it's going to be 1 minus 0.9982. So that's going to be 0.0018. All right, so now for our conclusion in context. So for the conclusion, it should be, since our p-value 0.0018 is less than alpha of 0.05, we reject our null hypothesis. We have convincing evidence that the mean IQ scores for students at the school is greater than 100. All right, describe a type 1 error in the context of this problem. So instead of writing it out, I'm just going to say it verbally. So remember, type 1 error is a false positive. So you think you found something, but really there was nothing to find. So in this case, we would conclude that the mean IQ score is greater than 100, but it actually isn't. That would be a type 1 error. A type 2 error is a false negative, meaning you think you didn't find anything, but you actually missed something. So in a type 2, this would be concluding that the mean IQ score, or that you don't have enough evidence to conclude that it's greater than 100, but it actually is greater than 100. You can also say concluding that the mean IQ score is equal to 100 when it's actually greater. All right, the next problem says the CEO of a large electric utility claims that 80% of its customers are very satisfied with the service they receive. A local newspaper thinks that the percent of satisfied customers is less than 80%. To test this claim, the local newspaper surveyed 100 customers using simple random sampling. Among the sampled customers, 78 say they were very satisfied. Based on this sample, is there support for the newspaper's claim that the proportion of satisfied customers is less than 0.80? Do a significance test and use alpha of 0.05. All right, so in this problem is about proportions, since I know it's giving us percents, and then the data that we collected is categorical because you're either satisfied or not satisfied. So we're going to identify the symbols. So P in this problem is what the utility is claiming, that's 0.80. P hat, we're going to do 78 divided by 100, which is 0.78. And then N in this problem is going to be 100 because that's how many they surveyed. All right, so writing out our hypotheses, this is a one sample proportion. So P is equal to 0.80. Our alternative is what we're trying to prove. We're trying to prove that it's less than 80%. P represents the proportion of customers who are satisfied with their service. All right, so now let's check our conditions. So the independent condition for proportions, big N, is going to be all customers. That's greater than or equal to 1,000. That's definitely reasonable. The normal condition, so this is going to do, we're going to do N times P, so 100 times P, that's 80. That's greater than or equal to 10. That's good. And then we have to do 100 times 1 minus P, which is 20. That's greater than or equal to 10, so that's good. That means we're approximately normal. And the random condition, it does state that it was a simple random sample. So our SRS is stated. All right, now let's go to our test statistic and p-value. So remember, with proportions, we always use z. So we're going to do p hat minus p, so 0.78 minus 0.80 divided by square root of p times 1 minus p over n. So that's negative 0.5. And now let's find the p-value. So we're trying to find the probability that p is less than negative 0.5. So when we're looking for less than, we're just going to look up negative 0.5 in our table. All right, so p-value for negative 0.5 is going to be 0.3085. So 0.3085, and we don't have to do anything special to that since we're looking for less than. Okay, so now we're going to interpret in context. So our conclusion would look something like this. Since our p-value 0.3085 is greater than alpha of 0.05, we fail to reject HO. We do not have convincing evidence that the proportion of satisfied customers is less than 0.80. All right, last question here, number 15. So it says a study of accident records at a large engineering company in England reported the following number of injuries on each shift for 1 year. The engineering company wants to know if there's good evidence that the injuries are not equally probable at different times of the day. So state the hypothesis, discuss conditions, perform calculations, and report your conclusions. All right. So for this particular example, we're going to be doing the chi-square test of goodness of fit because it's talking about equal probability at different times of the day. So the different times of the day is their categorical variable, and we want to see if the number of accidents is equally distributed or not. Okay, so let's first write out our null and alternative hypotheses. So remember, with chi-square test of goodness of fit, we write it out in words. So our null hypothesis is that they are equally probable. So injuries are equally probable at different times of the day. And then our alternative hypothesis is going to be just the opposites. They're not equally probable. So I'm just going to write not equally probable. All right, before we do our conditions, we need to do our expected count. So in this particular case, since we're doing equally probable, it's basically 33.3% for each one. But what we can do is we can add up all of these numbers and just divide by 3, and that's going to give us our expected counts. So the total number is 4636. So to get my expected counts, we're just going to do 4636 divided by 3, or basically taking 33% of that for morning, afternoon, and night. So that's going to be 1545.33. So that's going to be my expected counts. 1545.33, 1545.33, 1545.33. All right, so now I can do my conditions. So starting with my independent condition, big N would be all the injuries. It's greater than or equal to 10 times 4636. So since this is a large engineering company, there's probably been more than that many accidents at the company over all time. So yes, this is reasonable. For the random condition, so like I told you in class, this problem doesn't state that they only did a random sample, but for this particular case, we'll just say it's not met, but that's okay. I'm still going to have you do the conditions. Like I said on the test, it'll be more obvious that that condition is met. And then the last condition is that all expected counts are greater than 5. Greater than 5, and that is true. All right, so now let's do our calculations. It says include your table of expected counts, which we have here. So to do our, get our test statistic, remember we're gonna do the observed, so 1372 minus the expected 1545.33 squared over expected. And we're gonna do that for every single one. So the next one would be 1578 minus 1545.33 squared over expected. And then the last one is 1686 minus 1545.33. So when we add those all together, we get 32.94. So that's our test statistic. For degrees of freedom, it's going to be 3 minus 1, which is 2. So now we're going to just use the p-value calculator using that website. And when we do that, it gives me a p-value of less than 0.00001. So in other words, our p-value is very, 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 very small. So then we're going to write out our conclusion in context. So our conclusion is since our p-value is less than 0.00001, this is less than alpha 0.05, we reject the HO. We have convincing evidence that the injuries are not equally probable at different times of the day.